Many thanks to the organizers for their efforts, valiant efforts to bring all of us here. And yeah, it's very pleasant, informative conference. So this talk is based on 3 papers, all of them co-authored with Eugenii Shustin from Tel Aviv University, and also one of them with Polyavsky and Dylan Thurston. And 2 of these papers have already been published. One is being edited right now, still in preparation. Altogether, it's about 200 pages. So I will sort of just present. This is an advertisement for this project, just to maybe motivate some of you to look into the papers and see what's actually in them. So, and I will focus on this subject, this notion of expressive curves. And I will use this screen to point my laser pointer to. So if you are looking there, then you won't see it. The plan is first I will talk about these expressive curves. We will discuss the definition, the classification of these curves, and some examples. That's about half of the talk, and then I will attempt to connect it to various things that some of you care about, namely singularities of plane curves, links, in the sense of usual low-dimensional topology, and quiver mutations. So I will start with a theorem that many of you know. So it's due to Michel Rolle from 1691. And it says that between each pair of roots of a real polynomial, there is a root of its derivative, a critical point. There could be more than one. There could be some critical points outside those intervals, but there are at least these ones. Okay, so not many of you, probably only those who have been to this talk before, know that that Rolle actually proved it only for polynomials. In fact, he was a big critic of the nascent field of mathematical analysis, of calculus. He strongly felt that it was poorly justified. He thought it was some sort of, voodoo in the alchemy, talking about these infinitesimals and so forth. And he gradually, after maybe 20 years of critiquing it, admitted that there was some scientific content to it. But this theorem was proved for polynomials. And then Augustin Louis Cauchy in 1823 extended it to differentiable functions. And it's now viewed as essentially an analytic state. Now, here's the strong version of Rolle's theorem. What it says is that if we know our polynomial only have real roots and all of them are distinct, then not only does each interval between 2 consecutive roots contain a critical point, it contains precisely one critical point, and there are no other critical, not even in the complex domain. Okay. That's because if your polynomial has degree d, then this rule already delivers d minus 1 critical points, which is the number of roots of the derivative. So Cauchy's theorem is an analytic statement, as I mentioned. This is an algebraic statement. It relies on algebra in some. It relies on some secret sauce, which is, the extra condition that we have distinct real roots, but and also, of course, some fundamental theorem of algebra, right? So nothing like this is true for just differentiable functions. And so the notion of an expressive curve comes from the desire to generalize this statement to polynomials in two variables. I don't know how to do it in more variables. Okay, this is of course revisionist history. The real reason was different, but this is how we pretend that we got interested. So what happens there? So we have now a polynomial in two variables, x and y. It's a real polynomial, so it has real coefficients. Its roots are just the points on the curve, on the real plane algebraic curve, g of xy equals 0, right? So we know where the roots are, right? They are, know means we will look at a picture, right? And then just like in Rawls' theorem, we ask, and where are the critical points? Where they should be somewhere in between those roots. Well, okay. Well, first of all, there is a saddle at each self-intersection at each node. I assume that this is a nodal curve, so it can intersect itself, but only transversally and only double points. So, okay, so these are not smooth points, and therefore, G they must be critical points for G. And of course, also there is kind of a genuine Rawls idea, right? If you have a function which is 0 on the boundary of some domain, right, which is homomorphic to a disk or ball, a two-dimensional ball, just like in one variable, this is an interval, which is one-dimensional ball, right? It's at the end of that interval, it's 0. Right, of the sphere, so to speak, right? Then in between there is a critical point. Here, if at the boundary is 0 and it's non-zero inside, so this means it's either a cap or a cup, and then by compactness there is a maximum or a minimum, right? So there is at least one extremum inside each bounded region. And so the question is, how can we make this two-dimensional analog of the strong Rawls theorem? How can we ensure that there is exactly one critical point inside each bounded domain, no critical points outside, right, in the unbounded domains, and no complex critical points? And we know how many critical points a polynomial has, right? So it's like d-1 quantity squared, because we need to equate each partial derivative, which is of degree d. So partial derivative, if a polynomial is of degree d, each partial derivative degree d-1. So by Bezout, both of them, we want both of them to be 0. It's d-1 squared. Okay, so like naively, if we can count that many critical points here, then we can conclude what we want, but that turns out to be not the right state. This almost never happens. It's just, yeah. All right, so now here comes the notion. I call a curve expressive if you can read off its critical points from the picture. Okay, so the curve here is shown in black, and in red and in blue, you see the isolines, the level sets for various values. Positive if red, and negative are shown in blue, right? And you can see there is a minimum here, there is a maximum here, minimum here. Okay, it's a corollary of our main theorem that if you have a collection of circles, each pair of them intersecting at 2 points, then it will be an expressive curve. So there will be exactly one maximum or minimum in each of these bounded domains and nothing. So this is just an informal definition. And this can be viewed as a two-variable counterpart of the real rooted invariant polynomial, right? Which was necessary for the strong version of Ross. And of course, I just wanted to show you at least one non-example. So this is a union of two ellipses. And you take the left-hand sides of the equations that define them, multiply, then now you have your polynomial. And anyway, these are the level sets. You can see that there are two maxima here, and there is a saddle here. Okay, so there are two more critical points than the topology requires. And so this is not an expressive curve.
Two more critical? One more?
Two.
Two?
Yeah, there is a saddle here.
Oh, because of that. Okay, sorry.
Yeah, so two maxima in the saddle instead of just one max. Okay, because you have, a camel with two humps, there will be a saddle in between. So how can we just determine whether a given curve is expressive? So this will require some preparations. So now let's get formal. So G will be polynomial with real coefficients in two variables. It defines an affine plane algebraic curve in C2. We can only focus on its real points, which are given by the same equation, but in the real plane. And we call this polynomial or the curve C expressive. And by the way, why I call it expressive? Because it expresses, it's enough to look at that curve and it tells you sort of a lot more than meets the eye. It tells you where it's sufficiently expressive to somehow convey like where the critical points are. Okay, more than one would generally expect. Okay, so we want all critical points to be real, and we want them to be Morse, as they say, so non-degenerate matrix of second partial derivatives. Each bounded component of the complement we want to contain exactly one critical point, unbounded, contain no critical points, and we also like it to be an actual curve, sort of like be connected and contain infinitely many points. Okay, this set of the questions about the definition. It's a formal definition of an expressive curve. Now, I will also need a technical condition of regularity at infinity. So this is something that is going to eventually be satisfied more or less automatically, but just to state the theorem, I need to introduce it. So we have, you can always take a projective closure of a curve. So let's pass from a plane to P2. So there will be projective coordinates x, y, and z there. When z is 0, this is the line at infinity. And the complex plane is the complement of that. So now instead of G, a polynomial in x and y, we have a homogeneous polynomial in x, y, z, the usual way, right? You can homogenize G by inserting power of z into each monomial to make all monomials of the same degree. And now we have a complex projective curve, right? And we can assume, since we are just looking at the pictures, so that it is reduced. And of course, it would be silly if it contained L infinity. So exclude that. And now there is this technical condition that describes the behavior of the curve at infinity, how it meets the line at infinity. So basically, I want to control the critical points that escape to infinity. So suppose P is a point where both partial derivatives vanish. but they vanish, at infinity. So P actually lies at infinity. And then I want the intersection multiplicity of the two polar curves to be expressed by this formula, and this is sort of what you would generically expect. So this is mu of CP is the Morse number. It's how many critical points are lumped together at that location. And formally speaking, this is just the intersection and multiplicity of between the curve and the line at infinity. And this is sort of generically this will happen. This identity will happen. You need to work very hard for this to fail. In general, the left-hand side is greater than or equal than right-hand side, and in order to have to not have equality should be some rather exotic behavior. In particular, it doesn't happen in small degrees. Okay. So you can now forget what this says. But we will need another ingredient to formulate the main theorem. So I suppose everybody knows, or most people here know what a rational curve is, right? A curve is rational, it has a rational parameterization. So x equals some rational function of t, y equals a rational function of t. But now we want those rational functions to be polynomials. In fact, polynomials with real coefficients. Then we say that our curve is a real polynomial curve. So this is a special kind of a rational curve. And there is an intrinsic description of it. It just means that it has a unique local branch at infinity. So it means that your curve intersects the line at infinity at a single point, and at that point there is just one local branch. The germ doesn't factor. And there is a similar notion of a trigonometric curve, which is also a special kind of a rational curve. But now x and y are parameterized by trigonometric polynomials. And it's again a simple result, classically known, that this is if and only if that curve only meets the line at infinity at two not real complex conjugate curves. And at each of them, it doesn't, it only has one local branch. So that's a real trigonometric curve. Okay, so these are two special classes of, irreducible rational curve. Okay, so now our main theorem, which I'm not gonna even hint at how it's proved, says that the curve is expressive and regular at infinity if and only if it satisfies three conditions. First, every component should be either polynomial or trigonometric. Second, the only singularities that are allowed on the curve are real hyperbolic nodes, meaning points in the real affine plane where two smooth branches intersect transversally. And also we want the set of real points in the affine plane to be connected. Okay, so notice that all of these statements are conditions on the curve itself. So we only look at the set of roots of our polynomial, right? We say nothing about the behavior of the polynomial outside that set. Just like when we said that all roots of a univariate polynomial are real and distinct. It was a condition on the set of roots. Okay? And then somehow, knowing that the curve itself satisfies those conditions enables us to conclude something about the behavior outside the curve, right? The behavior of our polynomial outside is more precisely the location of its critical. Now, the most surprising part of this, when we discovered this statement, was that all the components are rational. Like, why in the world does this have anything to do with this analytic statement, that we want of expressivity? So, in particular, if there is just one component, right? Then this is saying, if we have just a polynomial or trigonometric curve, we just want to make sure that it doesn't have any other singularities other than real hyperbolic nodes, then it is expressive and infinity, right? And then you can take several such curves, and these will be the components of your future expressive curve, and you want to overlap them sort of transversally, right? And make sure there are no crossings, in the outside the real domain, and then we can draw the desired conclusion. So, right now, notice. Well, I want to note that an expressive curve, even though it's a nodal curve, it can have very complicated singularities at infinity. In fact, it typically does, right? Even a polynomial curve, right? I just told you, polynomial curve only intersects the line at infinity at one point, right? Because it's given just like a function of t, right? So when t runs to infinity, this thing runs somewhere to, right? But if it's a polynomial of degree d, it should, that curve should intersect any line at d points, including the line at infinity. So that intersection is like of multiplicity d. So there is a lot happening at that point. So it's highly singular. Okay. And in some sense, it's not surprising because we want lots of critical points to run away to infinity. So we want them to be concentrated at those points that we know how many there are, but like we want many critical points among the ones predicted by the zoo to be located in infinity. Yes.
Why do you require the curves to be connected?
It's a technical condition. Maybe we don't have to. It's not clear to me that this is like necessary, but in all applications, they are connected anyway. So, like if it's not connected, if we have like two circles, then in between there will be a saddle. So, typically it is connected automatically. Okay, and let me point out that the direction in which anybody ever is going to use this theorem is from the bottom up, right? Given a curve that satisfies all of this, because like how would you learn that a curve is expressive? It's not clear, right? So if all of these conditions are satisfied, then the curve is expressive and an infinity regular, which we don't care really about. So if you don't know what that means, it doesn't matter. Okay, this is only here to sort of convey the message that morally this is if and only if. Like we are not missing out on some nice curves that are expressive but somehow are not given by this construction, because they would have to be fairly pathological. So this is a rather restrictive property, as you could see, and it's kind of surprising that the zoo of these curves is actually quite big. So there are many examples, and now I'm switching to the discussion of those examples. When did I start? 3:45? Okay. Oh, you are. So take any nodal connected real line arrangement, that will be an expressive curve. This is actually easy to prove directly using convexity, because your curve is given by an equation, which is product of linear polynomials equals 0. So, and then, like inside each of these regions, it will be convex. And so it will only have one, because it's like the log of it is the sum of logs, and each log is constant. So, so this is an easy statement, but I wanted to present it anyhow. This is harder to predict. Okay, so this is the first non-trivial example, a series of non-trivial examples. I don't want to explain what exactly is required from these parabolas, but you can imagine, like, okay, maybe I should. Like, for example, like here, each pair of parabolas intersects at 4 points, I think. Oh no, this one and that one, it only intersects at 2, right? But the other two, so parabolas being conics, they intersect at 4 points. But we want the points that are not visible to be at infinity. So these two parabolas are co-oriented, right? Because they like share this line of symmetry. And so they intersect at that point in infinity, which is the same as that point, right? And in fact, they are tangent at that point. So it's both points are at infinity over there, right? So, and that's what we need, right, for expressivity, because we don't want them to because the point of intersection would be singular, and we want that to be visible in the picture, right? So if in particular real. So if we have two parabolas that, like one is like this and the other is like that, then, there will be like pairs of conjugate complex points at which they intersect, and that's not good. And indeed, there will be like a saddle here that we don't see or something, or a critical point with complex coordinates. Okay, circles, right? Why is this an example? Well, we have to recall the definition of a circle. What is a circle? A circle is a conic that passes through two special points at infinity, right? The points with coordinates 1 plus minus I 0. So every circle passes through those 2 points. That's why two circles can only intersect at 2 points, even though their conics should intersect at 4 points, right? That's because the other 2 points of intersection are those two special points. Okay, which is good. That's exactly what we want. So if we have a bunch of circles which intersect pairwise at 2 points, so we cannot have disjoint circles. They have to intersect. Once you have 2 points, the other two are at infinity. We don't care. Satisfies our theorem. So this is an expressive theorem. So in particular, if you take the polynomial that defines this collection of circles, so it's a product of these expressions like x squared plus y squared minus r squared, right? The product of such things, and equals 0. That's your curve. So that polynomial on the left hand side, you differentiate it. You don't take derivative with respect to x and with respect to y. These will be horrible equations. And the solutions of those equations will be the critical points. There will be exactly one solution like in each of these domains, and also at each cross. I don't know how to prove it just using calculus. It's just not, these regions don't have to be convex. It's not, like, how do you prove it? But it's true. Okay. You can take both lines and circles, right? As long as they, all their crossings are controlled, right? So any two lines should intersect in the plane, or else be parallel, in which case they intersect at infinity. That's fine, right? And each line must intersect every circle, right? So that both points are real, and each pair of circles should intersect at 2 points. And all of these points that I mentioned should be distinct. If that is satisfied, as it is in this picture, then it's an expressive curve. So again, each of these regions contains exactly one vertical. Okay. So in particular, like if you want to, solve an extremal problem or find a maximum, you know that there is maximum is unique in each domain. So, like you can run steepest descent or something, and you're not gonna accidentally run into some local maximum. So it might even be useful. I'm not sure. Yeah, that's not why we are interested in it. A generic cubic is not expressive because it's not rational, but a nodal cubic is, and then you can take several of them and you can throw in, and it's also a polynomial curve, and you can throw in some circles and lines if you want, and which I didn't do here. These are so-called Lissajous curves or Chebyshev curves, which are, either trigonometric, which is the case here, or polynomial, which is the case here, or union of the polynomial and trigonometric pieces. So these are given by like x equals cosine, some multiple of t, and y is sine of the same, a different multiple of t, right? Okay. And again, it's not hard to see that they satisfy the conditions about it. These are very fun examples. I spent quite a bit of time playing with them. So these are hypertrochoids and epitrochoids. Okay, so there is this spirograph toy. So you draw it like there is a circle that is moving along some other circle, and you put a pencil inside and you draw something. Okay, but you have to make sure that you get the maximal number of self-intersections that is possible for a given ratio, like there is a rational ratio of the diameters of the two circles, and but then like there is also where you stick your pencil in, right? And you need to stick it in the right place so as to get the correct number. So like the maximum here we have 5-petal hypertrochoid, and that would work, but if you just were lazy and did something like this, be careless. Yeah. You know what I'm saying? You could get like the petals would not be big enough to overlap, right? And this means that some of these self-intersections they went into the complex domain, and so that's bad. So they would be singular points outside the real plane. All right. So now confession time. So why were we interested in this in the first place? Because we developed this theory as a global counterpart of the classical local theory of morsifications. These are morsifications of isolated plane curve singularities. Classical theory developed by Arnaud and his school, and also more or less independently by Norbert Acampo in Switzerland on the other side of the iron curve. This was a rare case where Acampo was isolated from the main stream of modern mathematics because of the iron curve as opposed to the Soviet mathematicians. Okay, so it's a study of isolated singularities of algebraic curves. We study them in topological category. So not up to diffeomorphisms, and not in the smooth category, not up to algebraic, isomorphisms of algebraic curves, but in the most coarse possible setting, up to homeomorphisms. Okay, which is important. There is a substantial distinction between between the two settings. For example, when you have a when you have a quadruple node, transversal intersection of 4 smooth branches at a point, then every diffeomorphism is locally linear, and so it preserves the cross ratio between the 4 tangents, whereas topologically every such crossing is the same. So this in Arnold parlance, this means that this singularity is not simple; it has moduli, and are not classified all simple singularities, and it's an ADE classification. And moreover, the quivers, the Freudian slip, the Denkin diagrams that emerged from that classification were naturally oriented, so they were quivers. So it was natural to ask, like, why do we have ADE quivers arising in this theory, right? Nobody in the 50 years that passed since was able to find like a direct connection to Lie theory from this, between this theory and like representation theory. But maybe that's because they were looking sort of in the wrong place. It's because these things are oriented naturally, so maybe there is a connection to clusters. So that was sort of the impetus for the project, the original one. Now, when you study these singularities topologically, all the information is actually contained in the link of a singularity. So your curve is something one-dimensional on a two-dimensional plane, but since we work over complex numbers, it's actually something two-dimensional in a four-dimensional space, right? So your curve is a two-dimensional subvariety of a four-dimensional real space, and then you have some singular point. You surround that point by a little circle, little S3, sorry, not circle, sphere, S3, right? You intersect S3 with that two-dimensional thing, you get something one-dimensional inside S3. That one-dimensional thing is a link, right? Could be a knot, could be several components. And the topology of that link entirely captures the local topology of your singularity, because your curve is basically topologically just a code over that link. So this was understood already by Hegard and people like Zariski and Burrell, so more than 100 years ago. So all information is contained in this link, so we just need to figure out what the link is. So how can we compute this? Well, so Arnold came up with this ingenious idea of using morphifications. So first of all, we can always assume that our curve is real. Okay, so you can change coordinates so that the coefficients of our polynomial will be real numbers without changing the topology. Okay. Including a total real form. Total real form means that when you factor that polynomial, right, which is equal to 0 on the curve, into irreducible factors, each factor also has real coefficients. Okay, like for example, x squared plus y squared equals 0 is a perfectly legal real curve, right? It's a real one, but it factors into x plus I y times x minus I y, and those are not real. Okay, we don't want that. I mean, I do, but if the totally real form doesn't allow that. Okay. Now, what's a morphification? It's a local deformation of your curve, of the germ of your curve, that has maximum possible number of these double points of the crossings. Okay, this is an example. Let's take this is a very bad singularity. These are two, so it has two local branches, which each of which is a cusp, right? These are two kissing cusps, and they kiss you know, it sort of appropriately, right? So that the cuspidal tangents are parallel, right? They could be kissing at an angle. They're not good, right? Okay, and then when you perturb a cusp, you get a nodal cubic, right? It's easy to believe. And this is not a morphification because here we only get two crossings between the two nodal cubics, whereas here we get 1, 2, 3, 4, 5, 6, 7, 8. No, not 8. 6, because 2 of these are self-crossings. Okay, and this is a morphification. Okay, this is a somewhat informal definition, but I don't want to dwell on this. You can look it up in the paper. Okay, so it turns out that another definition of a morphification is that the critical points of this morphified polynomial are sort of expressed by the morphification in exactly the same way as in the case of expressive. So that was the original definition of our nodes, which we just took into the global setting. Okay, so basically we want all critical points to be identified by this picture, you know, saddles at the crossings and exactly one, and those saddles should be, you know, all at the 0 level so that you can see them, and the maxima and minima are 1, you know, inside each boundary region. Okay, that turns out to be equivalent to just having a large number of self crossings as possible. Okay. So our node student, Sabir Hussein-Zadeh, as well as Norbert Acampo, simultaneously, but not knowing about it, proved that such a morphification always exists. Okay, you just need to take a totally real form of your curve, and then, you know, there is a way to perturb it to get this. It's a conjecture, essentially, of Shustin's, although, you know, like we are both co-authors of it. Clear that he is an expert in this, not me. That in fact, any real form possesses a real morphification. Okay? You don't have to be totally real. Okay, let me explain to you if you wonder what do I mean by like any real form. So there are many real forms. Yes. How does that happen? Let me continue with the example that I already mentioned, a quadruple node. So that's a homogeneous singularity of degree 4. So this is 4 lines intersecting in a point. They can all be real. I mean, I took some specific 4 lines, like the coordinate axis, you know, and the 2 bisectors of the quadrants, right? But we could also have 2 real lines and 2 complex conjugate ones, right? When you multiply, you get a real polynomial, but the lines themselves don't have to be real. So this one is the totally real form, right? This one is not, and here we have 2 pairs of complex conjugate lines, right? So you always have a totally real form, but there are other real forms potentially. And they look, their morphifications look very different. So this is how they look like. So you have 4 real lines intersecting at a point, right? You shake it a little bit, you get 4 lines which almost pass through that point. So if you look under the microscope, it will look like this, right? Or if you have 2 real lines and then 2 complex conjugate lines, so the equation is x squared plus y squared equals 0. You shake it a little bit, you get x squared plus y squared equals epsilon squared. Oh, here it's t squared. So t is epsilon. Very small, right? You look under the microscope, you see this little circle, right? So, like, set theoretically, your curve x squared plus y squared equals 0 was just a single point, 0, 0. But that's an optical illusion because the curve is sort of in the complex domain, right? But when you emulsify it, that point grows and becomes a little circle, right? So, and of course, it could be that that circle intersects the other 2 lines, you know, in a different way. If you perturb it. And similarly, for when all 4 branches are complex, they, you know, come in 2 pairs, and you want those 2 ellipses to intersect at 4 points, because if they don't, this means that there are some other intersections in the complex domain, and that's not allowed. Okay, so these are the pictures. And Arnaud's idea was that this morsified curve actually contains all the information necessary to recover the topology of your singularity. Okay, that this sort of doodle, right, or Ocampo called them divides, these pictures, right? So each of these divides actually determines the topological type of the singularity. So let me explain to you how. And in particular, how can we tell that this is the same singularity, right? I mean, different real forms, but in the complex domain, it's the same. Well, we need to compute the link, right? We know it from that old observation that the link determines everything. So we need to figure out how to determine the link from this doodle, from this divide. If I view these pictures as expressive curves, because each of these pictures can be thought of as a picture under the microscope when I'm looking at a perturbed curve, you know, in the vicinity of my singular point. Or I can go far away and look at some curve in the plane, right? From far away, then this is like everything interesting happens in some small domain, and it's sort of the same portrait, right? But actually, the divides that come up are distinct. So there are pictures that come up in one context, but not the other, and vice versa. So what do these curves have in common? Well, it turns out that they also share the same link, the so-called link at infinity. Right? So instead of intersecting with a little sphere, I could intersect with a very large sphere, or actually the right thing to do is intersect with the tubular neighborhood of the line at infinity. And then I get a link at infinity. That link is entirely determined by what we call profile at infinity, meaning the singularities at those crossings of the curve with the line at infinity. Because everything interesting is happening at those points. And it can be checked that all these curves have the same profile. I mean, some of them go through, the profile is actually kind of clear. It's just 4 transverse intersections with the line at infinity at 4 distinct points. And therefore, it's the same link. Okay, so we can, by some topology, we can conclude that the links are the same, right? On the other hand, these links are determined by the pictures. So these pictures must have something in common, something combinatorial in common. Because only the topology of these pictures matters, not like the metric geometry is not important. So how to compute these links? Well, as I mentioned, we look at this curve really as a doodle called the divide. From a divide, we can construct something called a plabic graph by replacing every crossing by a roundabout. Then there is a construction due to Tomomi Kawamura, which we adapted to our needs, that associates a canonical link in S3 to any plabic graph. This construction is very similar to some earlier constructions that appeared in the literature. So this is an explicit combinatorial construction. Combinatorial, like it's a construction of a link, so there's some topology to it. And the link is actually constructed inside a circle bundle over the disk. So we start with a curve or a germ of a singularity. We get a divide. From that we get a plabic graph. From that we get a link. And Ocampo showed that this link is the link of the underlying. Okay? So it's not just an abstract statement that the doodle determines the topological type. There is actually an algorithm for computing the link. And his algorithm was different from ours, but it's an adaptation. So that's why I wrote that it's together with us. Because the way I presented it to you with plabic, I mean, obviously he didn't know about plabic graphs or anything like that. But it's the same, like once you know. And in the paper that is yet to appear, we prove with a lot of blood spilling that the same is true in the case of expressive curves. Okay? We recover the link of the curve at infinity using precisely the same procedure. Just using a different doodle, the one that we get from the set of real points of our curve. Okay, now since I'm short on time, so this is something that most of you have seen. Local moves for plabic graphs introduced by Postnikov. And it's not hard. Once you know that we have plabic graphs here, you check that what happens with links under these moves, and the links remain the same. These local moves preserve the links. It's not hard. You also know that every plabic graph determines a quiver in a standard way. And this quiver, it turns out, again, in retrospect, looking back at those papers, those Coxeter diagrams that they called them, and then people started calling them Ocampo-Gussen-Zadeh diagrams, are exactly the quivers of the corresponding plabic graphs. Okay, so everything matches beautifully. And of course, local moves on plabic graphs correspond to quiver mutations, as we know. So what kind of picture emerges? So we have these plabic graphs coming from curves or curves either in the local or in the global setting. And move equivalence preserves both the link and the mutation equivalence class. In our big conjecture, which we probably first posed like 10 years ago informally, and then it went into a paper and so forth, but we couldn't prove, or even, we proved many instances of it, but special cases, but not in general, that in fact this side and the link side and the quiver side are exactly like they know about each other completely. So if you know the mutation class of the quiver, then you know the link, the isotopic class of the link. If you know the isotopic class of the link, then you know the mutation class. We can prove it essentially for all known algorithmic constructions of morphifications. but we don't know it in general, like from some kind of conceptual sources. For example, what does it mean in our running example? So we can start with these 4 morphifications. For each of them, we construct a quiver. It's using the procedure that I told you about. I didn't write the roundabouts. I just used different rendition, but it's an explicit combinatorial rule, very simple. You can figure out what it is just by looking at the picture. And what's common between these 4 quivers? They are mutation equivalent. And any other quiver that comes from a divide of a morphification is not mutation equivalent. That we can actually prove, like a small case. And the conjecture says that this will always be true. Now, why can something like this be true, right? This is a reminder of how all of it works, right? We start with an expressive curve or an isolated singularity, get a divide from a plabic graph and then quiver or a link, and then move equivalence, translates into either mutation equivalence or transverse isotopy of links. And these things are supposedly mirroring each other, so there should be some kind of mirror correspondence between them. Well, the only explanation that sort of would enlighten this or prove it maybe is that there is actually some cluster algebra behind it, right? And that when we are choosing a different real form, a different morphification or something, right? We are just changing sort of a way of defining that cluster algebra by passing to a different seed or doing something else. Okay? And if there is an intrinsic cluster algebra, then that would explain everything. That it doesn't change, the link is determined by it, and so forth, right? But nobody has any idea how to define it, let alone prove that it has the desired properties. So that's maybe one of you will figure that out.
These are other equations.
Oh, I was wondering, is there a version of this in 3 dimensions?
Wondering too. I don't know. It just seems very hard. Even this business of morphifications for polynomials in 3 variables, it's sort of very non-intuitive. And people worked on that, but it's just like the entire singularity theory becomes much, much harder. Yes.
I would like to kind of reverse the question. Do we have one group analog?
Probably. I mean, I doubt there is anything interesting happening there, but that's a good question. Yeah. Just because it could maybe suggest some right, and then like analogize from that.
Here, the question.
Whether for polynomials in 1 variable, there is sort of something interesting going on, so that if we sort of understand that, then this would suggest like how to generalize. But like 0-dimensional spheres that are much simpler than 1-dimensional spheres, right? Yes.
Is there anything you've noticed for like finite type quivers or special quivers that might show up?
So for finite types, we proved everything that there is to prove, because and of course, in the notion of finite type exactly matches our knowledge notion. So all of that is kind of works as one expects. But I wouldn't say that there is something new that I learned, like for the purpose of like cluster theory or something. Right. It's just a nice family. And also like some other types, like affine exceptional types and extended affine, also show up in these contexts. And we looked at some other sequences series of examples, doesn't, I mean, yeah, I couldn't really extract anything new just for people who outside this area, so for them to sort of take home as a tool. But that's only, I think it's primarily because we don't have an explanation. We don't really understand what's going on here. Basically, the instances in which we proved our theorem are the instances in which everything can be computed in some form. And then the results of the calculations match. But like why they match, that's, yeah.
So since this is two-dimensional, I can split any of these curves into complex. I can factor them into like complex linear terms, right? Is there anything that
No, you cannot. It's in two variables. Like a generic polynomial in two variables doesn't factor. Like, I don't know, x plus y plus 1, or linear, okay, x square plus xy plus y. No, they're not homogeneous. I mean, they will, if they're homogeneous, then 3 variables. But if 2 are, I mean, if it factors in 3 variables, then you set z equal to 1, it would factor in 2 variables. So you can't really trick it away. Yeah. Yeah, no, it's not, it doesn't factor.
Right.
So like the analog of fundamental theorem, yeah, it doesn't apply.
The quivers are finite mutation type, right?
Say it again?
The quivers are finite mutation type that appear because the.
These happen to be, but in general, no. No. No, in that example, first of all, is not simple because it's like extended and fine, but it is finite mutation type. And but in general, they're not. But it's thank you for asking, because it's natural to ask like what is special about these singularities, because we know from sort of the cluster side that these are sort of maybe not simple, but hey, sort of, right? They're not that bad. And so it turns out that indeed these correspond just by looking at the lists, they correspond to so-called unimodular, it's a terrible term, situations where there are moduli, it's not a simple singularity, but there is like only one parameter, right? Like the cross ratio in this example, right? There is only one parameter, you know that parameter, the smooth type of your singularity. So why is that? I don't know. Maybe there is some, because I don't know like what's at the heart of this phenomenon. But indeed, like the simpler the quiver is cluster theoretically, the simpler is the singularity. Again, so there are all sorts of writings on the wall that something is going on, but I don't know.
Thank you again.
Thank you.